back to the session, right. So, in the last session we discussed about the basics of Nyquist plot, right, and we had seen the basics of principle of mapping, and then we had seen the principle of encirclement, and now in today's session we will discuss how these two principles help in to determine the stability of Nyquist criteria. Okay. So, before initiating we would like to see the basic summary of previous lecture, so that we can connect the previous concept with the Nyquist plot, okay, and then we will explore the concept, or you can say steps which we will use to construct the Nyquist plot. So, we would like to see the basic summary from previous lecture. So, the previous lecture we had seen, if in a plane we have taken any pole, suppose here, and if we encircle this pole in clockwise direction, okay, then what will happen in GS HS plane? Suppose GS is given by 1 over S plus 1, then it will result in encirclement of the origin in anti-clockwise direction. Okay. So, here it will encircle the origin. So, last time we had seen that I had taken a certain points of this contour, okay, and then I mapped this point in the GS HS plane, and then what we were getting, if a contour is covering this pole in clockwise direction, then in GS HS plane it will cover in counterclockwise direction or anti-clockwise direction, that you can see, right. It will encircle the origin. In the same way, if we talk about 0 in the S plane, if we cover a 0 in clockwise, then we will get in GS plane encirclement of the origin in clockwise, right. So, this concept we had seen in the last lecture, and one more concept we had seen, that if in the GS plane, if this is my pole and it is covered by or traversed by a contour in clockwise direction, then the angle contribution by this pole would be minus 2 pi. In the same way, if this scene is happening with any 0, then the angle contribution would be plus 2 pi. So, this concept we had seen, if any 0 and pole lying outside this contour, and if we calculate their angle contribution, it would be 0. Okay. So, we had seen this thing in the last lecture, and we had seen in the Nyquist criteria, we would like to map our whole right hand side plane, that is RHP. So, we are scanning whole right hand side plane, and we are keep looking for all the zeros and pole lying in right half plane. So, we are taking a curve, a contour which radius is r tends to infinity, and it will cover the entire right half plane. If any pole is lying in the right half plane, so what will happen in 1 plus GS HS plane, a contour would be there which will encircle the origin. So, number of time this contour encircling the origin, that will tell us the number of poles lying in the right half plane. Okay. So, this thing we have done in the last session, and this thing we have done, that if we calculate 1 plus GSHS transfer function. So, we will get this expression, and if we calculate a normal open loop transfer function, this will be the, you can say, expression. So, here if we compare the open loop and closed loop transfer function, so ds plus kns basically giving us the closed loop poles, okay, and this ds basically this is open loop pole, right. So, this is open loop pole, right, and this denominator giving us the closed loop pole. So, when we calculate the 1 plus GSHS, we can see ds plus kn is coming in the numerator, which is equivalent to zeros of quadratic equation, and it is also giving us the closed loop pole. Okay. So, we can say its numerator part will give us closed loop pole. Okay. In the same way, the denominator will give us closed loop, open loop poles. So, here we had seen the summary, the closed loop pole is equal to zeros of quadratic equation, and open loop poles are equivalent to poles of quadratic equation. It means, if I am writing the quadratic equation in terms of z and p, so this will gives me the closed loop pole, and this will gives me open loop pole. This concept we had seen in the last lecture. Okay. So, here if we see that encirclement in 1 plus GS HS plane was happening around the origin. So, if we talk about only GSHS plane, then whole curve will shift around this point -1, and then this would be our critical point, and we need to observe encirclement around -1 in GSHS plane, right. What it means? If one encirclement around -1, it means one pole is lying on the right half plane, or if encirclement is happening maybe because of any 0, then 1 0 lying in the right half plane. So, this concept we were getting from the previous session, and to obtain the stability criteria we are saying n equal to p minus z, where n is the number of encirclement around -1, p is the open loop pole lying in right half plane, and z is basically the number of closed loop pole lying in the right half plane. So, you can see here I am saying z is basically 0. So, this is giving us closed loop pole lying in the right half plane. Okay. So, this thing we need to observe, and this is the Nyquist stability criteria that we have to use in this session. Okay. So, here one example. Suppose in GSHS plane what is happening, this contour is covering a pole -1 and it is encircling in clockwise. So, whenever we are moving clockwise, this encirclement is how much? Number of encirclement is n equal to -1. So, what information we are getting from here, right? When n is equal to -1, so n is given by p minus z. If open loop pole does not lie in right half plane, then we can say here value of p is equal to 0 and z is equal to 1. Okay. It means if open loop pole does not lie, so we can't say what would be the value of z, we will calculate the value of z, and from here p equal to n minus z, okay, and here we n equal to p minus z is here, and p is 0 minus z, from here n is -1, so we can say z is equal to 1. So, z is equal to 1, we are calculating from n equal to p minus z. It means one closed loop pole lie in the right half plane. So, basically what we are doing, we are observing here closed loop pole stability, right, and this closed loop pole should be 0 in right half plane for stability. Okay. This thing we need to observe here. The same way when we go for second curve, so here this pole -1 is encircled in anti-clockwise one time, then anti-clockwise second time. So, here n is +2 because we are moving in anti-clockwise direction. Always remember, whenever we are moving in anti-clockwise, sign would be plus. Okay. So, n is +2 from formula n equal to p minus z. So, right half plane I am assuming that open loop pole is 0 minus z 2. So, here I am getting what? Z value is equal to 2, right. It means what is happening? It means two poles lying in the right half plane. If I have to make the system stable, right. So, what is the condition? My z value should be equal to 0, and how it is possible to make it 0? If my value of p is equal to 2. It means if two open loop pole lying in the right half plane, then value of p equal to 2, and in this case if I put in the expression n equal to p minus z, n is here +2, my two open loop pole lying in the right half, and z would be, we need to calculate, so z would be 0 here. It means my system would be stable. Okay. If we do not make any two pole in right half plane, then my system would be unstable. In the same way, when we come for this case, so here how many encirclement around -1? It is 0. So, n equal to p minus z, and how if I assume my open loop pole in right half plane is 0, it means n is 0, p is 0, z would be 0, and this will be the stable system, right. What is the summary? We need to observe this point -1. If it is encircled, then we have to observe how many times. At the same point, we need to observe is there any right half pole, right, and if right half pole is present, then we can estimate its stability. If it is absent, then we can directly say okay, this would be an unstable system. Okay. So, we would like to understand this concept using the following Nyquist plot. So, before starting the Nyquist plot, we would like to see the basic steps to construct the Nyquist plot. For that purpose, we need to construct here a Nyquist contour or a Nyquist plot. Okay. So, here we need to do this mapping in 1 plus GS plane. Okay. So, here we need to do this map S1. So, in step S1, what we need to do? We need to draw the polar plot, where omega is varying from 0 to infinity. Okay. So, this is my step 1, and whenever we are doing this step 1, it means we are mapping our S1. So, this is my S1 plot of Nyquist contour or Nyquist path. So, this is my step 1, we need to plot polar plot with respect to given GSHS, okay, and then we will get plot of or map of S1. So, this is equivalent to a Nyquist contour that we are making in GSHS plane in the positive axis. Okay. So, it is lying, you can say, in plus 90 degree phase. Okay. This is the map S1. In the same way, what is my step S2? My step S2 is here, we need to replace S by limit r tend to infinity r exponential of j theta. This is the basically magnitude, and this one is the phase, you know it very well from the concept of complex number, where theta is varying from plus 90 to minus 90. It means in the GSHS plane, what is happening? This curve is going like this from plus 90 to minus 90. We are making this radius r tends to infinity. Why we are making this radius infinity? So that we can scan entire right half plane for zeros and pole occurring in the right half plane. Okay. So, that is why I would like to cover entire right half plane, so that I can cover all the poles and 0 lying in right half plane. So, that is why in the Nyquist plot in step 2, we are making this contour, that is map of S2. So, this map S2 is what? This is basically my second step. So, this would be, you can say, 1 plus GSHS plane. Okay. In the same way, what is step 3? We need to draw the inverse polar plot, and this will be the step 3 in Nyquist contour. Okay. So, here what we are doing? We are doing mapping from minus 90 to 0 degree phase. So, this plot will equivalent to the inverse polar plot. It will start from omega equal to minus infinity and it will terminate at 0. In some textbook, if you open, you are getting this value from minus infinity to minus 0, and whenever you are doing the map of S1, then range would be from 0 to plus infinity. Okay. 0 plus or 0 minus, they are equivalent to 0. So, you can take it 0 or 0 minus, it is up to you. Okay. It means in the map S3, we need to plot inverse polar plot with frequency variation from minus infinity to 0. Now, we need to move for the step 4. Step 4, we are doing this plot around this origin, you can say this plot is here, and we are moving from minus 90 to plus 90. Okay. So, why we are doing this? So that we can avoid my poles at the origin. Okay. And what is the radius? The radius of this curve is tends to 0. So, it is a very small detour we have to take, so that we can exclude any pole lying at the origin. Okay. So, whenever my single pole lying at the origin, then my system is not unstable, we know that. So, that is why we are not covering the origin which is having the pole. Okay. So, if we combine all the map S1, S2, S3, S4, then we will get this Nyquist contour, and this Nyquist contour we will use to determine our stability in frequency domain. Okay. So, this is map S1, map S2, S3, this is the basically S3, and this is map S4. Okay. So, here it is we are considering that my single pole lying at the origin. What will happen if my pole lying on this imaginary axis? This case would be a marginally stable case. Okay. So, in that case, what changes in the contour will come? In that case, I will assume my poles are lying at the imaginary, suppose some pole lying at the origin also, then my contour will move like this. I need to increase the number of contour and I need to ignore these poles coming in the imaginary axis. Okay. So, this will be our reference Nyquist contour, it will change like this. Okay. So, we need to consider this map of this curve, suppose it is S4, this is S5, this is S6, and in all the curve we have to assume our radius tends to 0. So, this is we are doing only to avoid poles lying on imaginary axis. Okay. So, this is our reference contour. We now would like to see how we can use this contour to solve the Nyquist plot. So, here we are taking on generalized GS open loop transfer function GS equal to k over s plus 1 over s plus 2. So, again here with the help of open loop transfer function, we are observing the stability of closed loop system. Okay. So, for reference I can draw my Nyquist contour, where step 1 if you remember polar plot, step 2 this curve of radius r tend to infinity, step 3 we need to plot polar plot, and step 4 if any pole lying at the origin. Okay. So, one thing I forgot to tell you, that step 4 is only valid, or you can say this step 4 is invalid when no poles lie at the origin. Whenever there is no pole at the origin, we need to skip the step 4. Okay. So, here this is my GS open loop transform is given. So, first I need to map here S1. So, for map S1 what we need to do? We need to draw polar plot for this function. So, we had explained a lot of example for polar plot in the previous session. So, we can directly plot this thing. This will come like this because it is type 0 and order 2 type system. Okay. So, this will be the polar plot corresponding to this. This is the map S1. Now, to map S2, what I need to do? Here in the transfer function, I need to replace S by R exponential j theta. So, this is my transfer function S plus 1, S plus 2. So, I will replace S by R exponential of j theta, where R is tending to infinity. It means S is going to be a very big parameter because S value is going to infinity. So, we can say S value as compared to 1 is very high. So, we can neglect S here, this will become k over S. The same way if we see the S plus 2, again if S is tending to infinity, its value is very high as compared to 2. So, we can neglect here 2 also, this will become dot S, that is k over S square, right. So, now we need to replace here this S by limit r tend to infinity r exponential of e j theta. So, here my GS would be given by k over S square equal to k over limit r tends to infinity. Here instead of S, this will become r square exponential of 2 j theta. This will come. Okay. So, here this r is infinity, this will become k over infinity multiplied by exponential of minus j 2 theta, or this will give us 0 dot exponential of minus j 2 theta, where 0 is magnitude. It means our magnitude is 0, this plot will occur at origin. Okay. So, this is my step 2 or sorry map S2. So, this map S2 you can see in the Nyquist plot, it is going like this. So, this curve is 0 in this figure. Okay. In the same way we need to go for map S3. So, S3 is what? Inverse polar plot. You can see this map S3 is inverse polar plot, and this inverse polar plot you can directly draw by observing the normal polar plot. You need to draw its mirror image. Okay. So, if I draw its mirror image, it would be come like this. You can say this will come like this. So, in the previous case here my omega was 0 and here at the origin my omega was infinity. If you see or if you remember the concept of polar plot, in the same way it will start from omega equal to minus infinity and it will terminate at omega equal to 0. In some textbook it is also given minus 0. So, it is optional. So, here direction of plot would be like this. So, that is the map S3. Now, for step 4 we would like to see, is there any pole at the origin in the GS? No, it means we do not need to plot here S4. Okay. So, now we would like to sum up all those things, it means step 4 will not exist. So, this plot would be in GS-HS plane, this would be the imaginary of GS-HS and this would be the real of GS-HS. HS is unity, you can say it is GS plane also. So, here my first S1 map is here starting from omega equal to 0 terminating at omega equal to infinity. Then my S2 is at the origin. Now, my S3 is the mirror image of it starting from omega equal to minus infinity and terminating at omega equal to 0. So, this is the Nyquist plot. Now, after doing this, what we need to do? We need to calculate the stability by observing this condition n equal to p minus z, where we know that n is number of encirclement around minus 1. Okay. P open loop pole, right. So, if you see the open loop pole here, so open loop pole in right half plane 0, there is no open loop pole in the transfer function. If it is exists, then you can say it will be in the form of s minus 1 or s minus 2, s minus 3, then we can say open loop pole lying in the transfer function, but here there is no open loop pole. So, we can say here our value of p is equal to 0. Okay. Now, n you can see this plot is touching the 0 axis and going above from here, it means it is not touching this real axis. It means I can assume minus 1 anywhere, it will not cut this axis. It means this plot we can say number of encirclement around minus 1 is 0 and we can say here z is equal to 0, right. If z is equal to 0, so we can say our system is stable. Okay. In the same way we can take a second example. So, here we are considering one pole at the origin. Okay. So, step 1, first I would like to draw here my reference Nyquist contour. Okay. So, my step 1 is plot polar plot, step 2 put r tend to infinity, step 3 we need to draw inverse polar plot, S4 we have to make r tend to 0. Okay. So, to map S1 we can say this is type 1 and what is the order? Order is here 3. So, in that case because there is no 0 and no pole lying in the right half plane. So, I can directly draw polar plot from previous lecture, you can see the polar plot lecture, you can directly draw this plot will come like this. Okay. So, here my omega is 0 at this point and here my omega is infinity, this plot is going like this. The same way to map S2 we need to replace S by limit r tend to infinity, okay, and here you will write r exponential of j theta. Okay. So, what is the value of theta here? If you see theta is varying from plus 90 to minus 90. Okay. This is the value of theta. So, here if I put this thing in this GS, so this GS is given by k over s multiplied by s plus 1 multiplied by s plus 2. Okay. So, here if I put s is going to infinity, this will remain s, here s is very high as compared to 1, this will become s, this s is very high as compared to 2, this will become s and this will give us k over s cube. Again this in the denominator what we will get? G is equal to 1 over limit r tends to infinity r cube exponential of 3 j theta, where theta is varying from plus 90 to minus 90, or you can say plus pi by 2 to minus 90 minus pi by 2. This is the range. So, here r is infinity 1 over infinity, and this will give us 0. Again our map S 2 will be at origin. Okay. In the same way, we need to map S 3 inverse polar plot. This would be like this, start from omega equal to 0 and omega equal to infinity. If we combine all the steps, so we will get a plot like this. Okay. So, we have not done the step mapping of S 4. So, we will do step S 4 in the next lecture. Okay. So, thank you for today.